Welcome to Sail America's 2020 Pacific Sail and Power Boat Show Seminar Series. Today's webinar is titled Weather Basics with Jeremy Davis. Understanding the importance of weather is critical to planning a voyage. Jeremy's presentation will provide a general introduction to weather basics, including discussions on climate, air masses, reading observations, radar and satellite interpretation, and sources of weather information important to the mariner. Jeremy is a yacht operations manager for Weather Routing, Inc. He has been employed by Weather Routing for the past 20 years, where he provides customized weather forecasts and routing advice to clients worldwide and supervises the forecast center. He is a 2000 graduate of Linden State College in Vermont. Jeremy Davis, welcome, and thank you for joining us.
Yeah, thanks for having me, and I'm looking forward to giving this presentation. We'll be talking a little bit, you heard about some of the topics there. We're going to talk a little bit here about weather basics for sailors. We're going to go through a whole bunch of different topics here and kind of give you, everybody that's watching this webinar, a nice broad spectrum of some weather features. And we'll cover quite a lot in it, but the good thing is, of course, you can go backwards and forwards and kind of be able to see different sections again if you needed to recap what was learned within those. So here's some of the topics that we're going to be discussing today. We're going to be looking at, what is weather and what is climate. There's a difference between the two of them. We'll tell you a little bit about how to interpret different charts and maps and surface analysis. Surface pressure. We'll be talking about how to interpret observations, radar and satellite data, cloud progression, ocean currents, professional sources of weather, and some concluding thoughts within those. And I'll also talk, also about choosing best weather sources. So basically, the first question is, if we just kind of boil it all down to, is what is the driver of all weather across the world? And the main thing that starts all the weather is the sun. That is the driving of all weather. It produces uneven heating throughout the earth, which allows for uneven heating and cooling, and that's what causes different weather features to exist. When we take a look at the sun, kind of looking at a very basic diagram here of the sun kind of sending its energy here, radiation towards the earth, you can see in different parts of the globe here, you're going to have more direct sunshine that we have closer towards the equator. And we're going to have more indirect sunshine the farther north that you go. Of course, with the seasons, this will all change, but the less insolation, the least amount of radiation reaching the northern latitudes or the far southern latitudes results in generally cooler temperatures there, and while closer towards the equator with a more direct recipient of the sun's energy will typically be warmer. So the heat becomes redistributed. And with weather patterns and weather features out there, a lot of it is pretty much looking at, the redistribution of heat and cold throughout the planet. So the cold air across the northern climates here, the polar and Arctic regions, that's going to have a tendency to move south. It's colder, it's more denser air, it's going to tend to move south. The equator has a lot warmer air that's also tending to head up to the north. And so it's trying to redistribute. So the colder air is trying to balance out the warmer air to the south and vice versa. Same effect here in the southern hemisphere. So it's when the two of those combine that we start to get our weather features and factors that we all know about, lows and fronts and high pressure areas, for instance. And there's different kinds of weather features that we have out there, and basically called air masses. And there's different ways that we designate these air masses out there. To the north, they're typically called of polar origin. So we kind of look at what is the origin of these air masses. Is it originating over the tropics, or is it originating over the more polar regions, as we kind of showed there with that distribution map? So across the northern hemisphere here is an example. You can see where the different air masses typically originate. So they're typically done again over the continent or over the oceans and over the poles or over the tropics. So for instance, if we look off into the Gulf of Alaska here, this is what we call a maritime polar air mass. So we look at the difference between where it's coming from. Maritime air, it's coming over the ocean. Polar, it's coming in from far northern latitudes. So an air mass is a large group essentially of air that has similar properties within it over a very large area, and these are moving around the globe at all different times. It's the boundaries of these air masses that give us our frontal systems out there and our transitions into different weather patterns. If we look over toward the North America, over the central part here, you can see continental polar. So this is air that's originating over the continent. In this case, let's say over northern portions of Canada, moving off to the south and east. Farther to the north, we have Arctic air developing over the continent here, over across far northern North America. Over the eastern coast US, we also have maritime polar air masses, similar to what we find over the Gulf of Alaska. Down to the south, where we have tropical air coming in, we look at that as being maritime tropical, so the warm and humid air that we get over the Caribbean or the Bahamas, the Gulf of Mexico, moving off to the north. We also get that here across the eastern parts of the Pacific Ocean, particularly during the summer months. When we look over inland areas here, this is continental tropical air, so this is hot, dry air, essentially, that is over landmass where it has developed in there. So all these different air masses have different properties to them, whether they're humid, whether they're dry, whether they're cold, whether they're warm, and it's where they move and kind of bump into each other that we get a lot of our weather systems. So again, they produce the fronts and storms. The larger the difference in the air masses, the stronger the systems can be. So if you have very cold Arctic air moving into very warm, humid air that we can get in the central part of the country, that can produce big, strong fronts and produce some of the tornado outbreaks that we can have. And again, it's the movement into and out of these air masses which produces our weather. And then climate versus weather. A lot of people can get these mixed up a little bit, but what to remember is about climate is that it's the average weather that takes place over a long period of time. It's kind of describing the climate, the long term. What is a typical year like across a certain region? And the globe has many different kinds of climate types. And this little fancy map here kind of shows a little bit of that, showing the different kinds of climates that we can see here across the world. And there's different letters and designations. And you don't need to worry too much about these. But what this shows is, where is there a similar climate? So if you look here off to the West Coast, you can see, that's more in the green here. That's a sea climate. That typically is like a Mediterranean climate. Here in California, you're familiar with that because the winters tend to be kind of wet and on the cool side, but the summers are very dry and warm. So that's how one of these climates that can be described here. It's a similar climate. You can see the same coloring scheme here in the Mediterranean that we have that too. There's also other parts of the world in South America that can have similar climates. So there's different ways you can kind of look at the globe here and kind of see where some of those different climates are. Surface charts, we're going to talk a little bit here about different weather features that we can see on these charts. This is just as you're doing a weather briefing, perhaps before you do a trip and you kind of want to know a little bit about what's going on in the world of weather out there, and kind of knowing how to read these maps can also help to give you a self-weather briefing out there. So we'll talk a little bit about highs and lows, cold and warm fronts. We'll talk about tropical systems and troughs of low pressure. And again, knowing where these systems are can also help you to do a self-weather briefing when you're preparing to do a trip or a voyage. Let's take a look at this surface map here. There's a lot of different pieces of information that are on this map, but there's a lot of good stuff here that you can kind of learn here on this different satellite map. We have frontal boundaries here. There's got a cold front coming in across the Pacific Northwest. We have some troughs of low pressure, heat lows over Nevada. We have high pressure kind of coming down across the northern part of the US. We have areas in green here that are precipitation. We have lines on here that are isobars, lines of equal pressure, and I'll be showing you a little bit about what all of these features are here coming right up. So what is an area of high pressure? High pressure here, we'll take a look at that. And high pressure is an area of high surface pressure. These are transient, which means they can move around quite a lot, or sometimes they're semi-permanent. You have a big high pressure area in the eastern part of the Pacific Ocean, several hundred miles off to the west of California. That's a frequent weather feature that we have out there. It's semi-permanent, which means it goes up north, it can move a little bit south depending on the time of the year, but essentially there's always kind of a big high out there, and that's what gives trade winds, for instance, that go all the way out to Hawaii, if you want to look at that, northeasterly winds on that, and also keeps more southwesterly winds on the north side of the system. So you can really see on the high pressure here, the circulation here along that kind of flowing in this fashion here. Along a high, it's going to flow clockwise around that. And it's going to see calm weather near the center of the high out there as well. So if you're in the center of the high and you're on a vessel and you're in the center of that, you're typically going to see some very light winds and lighter conditions. If you're on the periphery of the high pressure area, that's where you're going to see a lot more higher winds outside from that. And we'll take a look on the surface maps, and it's just easy to find a high. They're labeled as an H, and it's a blue H on almost all maps. In this case, it's showing one of those areas of high pressure that's kind of dominating out across the eastern Pacific Ocean. Now, the isobars, the lines of equal pressure, are typically found around these high pressure areas. So if you follow this brown line here, that's going to give you the surface pressure. It's going to be about the same, 1,020 millibars here. And if you go anywhere along the line, that's going to show you the same air pressure. So in this case, the same air pressure off the coast of Oregon here is the same surface pressure over western portions of Idaho. Low pressure areas are the opposite of highs. They're deeper and stronger, which means the lower the pressure is, the stronger they are, the more intense they are. They flow in a counterclockwise direction, the airflow around it, so it's going in the northern hemisphere in this fashion. The isobars, those lines of equal pressure, are typically tightly packed together near the center. And near the center of these systems, that's where we typically see our stormiest weather. So in most cases, if you're out sailing out at sea, you typically want to be avoiding low pressure areas, especially if they're on the stronger side, if you can help it. Low pressure area here on this map, looking at that same surface map. In this case, it is located here over Vancouver Island. And again, note the lines of equal surface pressure are closer together with precipitation. You can really see how it's closer together here with this low. While when you go to the high, notice how the center of this high pressure ridge here, those the lines of equal surface pressure here are much more farther apart. So typically going to have higher winds where these isobars are closer together than when they're much farther apart. So you can see the difference between the low pressure area and the high pressure area. So it gives you an idea. When you look on a map like this and you see all these isobars, when they're tightly close together, packed together, that's where you're gonna have your highest winds. In this case here too, we'd also see them over Montana. You can really see how tightly packed they are there versus off the West Coast where they're broader here in this high. Cold fronts, they are the leading edge of colder air moving into warmer air. Typically along a cold front, you're going to find showery and squally weather. You're typically going to see winds kind of veering around from the south to the west to the northwest behind them as the frontal passage moves through. You can see strong winds near a front, and the blue triangles will show the direction the front is moving into. So when you see a front like this, the triangles just aren't for decoration. They do actually tell you where it's going. And in this case, you can see this is kind of pointing off to the south and east. So you kind of point where the arrows are going, and that's the direction that the front is moving towards. On this map here, we can see a cold front here moving into the Pacific Northwest coast. Again, you can see it with the triangles. They're indicating the motion with that. They're pointing in the direction it is moving towards. So you can kind of see where that front would be moving inland. This front here is kind of a backdoor front over portions of Colorado and New Mexico. Strong high pressure to the east of it is pushing it off to the southwest. So you can kind of see that front is actually kind of moving in the way we don't normally see them, which is off to the south and west, because that cold air is so dense coming in from that Arctic air to the north. It's pushing it off to the south and west. Warm fronts, they are the opposite of cold fronts. They're the leading edge of warm air moving into cold air. You typically see steady precipitation along a warm frontal boundary. Humidity will increase when the passage of that front goes through, and temperatures will often jump as well. Winds typically will veer from the northeast to the east to southeast. So ahead of the warm front, they're coming in from the northeast. Then as it goes by, east and then southeast, typically behind it. High winds are rare during warm frontal boundary passages, but they can happen. And those red semicircles here will help to show you where the direction of that is going as well. So while the cold front has its triangles pointing in the direction it's going to, the warm front will have the opposite, and you can see where they're moving to in this case, kind of looking in that direction. Warm front here on the map, you can see that has moved into Washington State. Again, it's connected to a cold front here. So you're seeing some showery precipitation here out ahead of it. There'd be warmer air trying to move in to the south of it, and it's cooler air here off to the north and east of it. It's another warm frontal boundary here off the east coast of the US, also showing the precipitation on the northern side of that, where that warm air is coming in over the colder air, condensing out and causing precipitation in there. And you can see the direction it's moving to, because it's the direction of the semicircles are pointing towards. Stationary fronts, these are frontal boundaries that have little discernible movement. They can often serve as a focus for rain and precipitation. And you can see how the movement of that, how the colors here, It's a cold front and a warm front essentially combined. It's like a hybrid of both. It's not moving. So the colder air is trying to push south. In this case, the warmer air is trying to push to the north. Neither is winning, and hence it is the reason why it becomes stationary. In this case, you can see a stationary front here over Wyoming. That's another, go right here over Wyoming. You can see that stationary front. So in that case, that portion of the front is not really showing much movement. Occluded fronts, this is a kind of front that you're probably not as familiar with. They occur when cold fronts kind of overtake warm fronts. And it pushes the warmer air aloft, and it can mark the boundary of colder air moving into cool air. So it's not warm air into cold air, vice versa. It's colder air moving into cool air. And the triangles and the circles are also pointing in the direction. Now, what's interesting with this one here is you can see on this image here, it's moving off to the north here. It's a mixture of a kind of a cold front and warm front that's actually moving. So again, colder air going into cooler air, and the red and the blue kind of make it purple. So you can kind of see it's kind of a hybrid with that. So in this case here, there'd be colder air on the south side of it, cooler air on the north side. It typically produces periods of rain or snow, depending on what part of the country you're in. This other surface map, it's a different one than the last one I showed, but it does show an occluded front here moving into portions of Oregon. So in this case here, it's cool air over Oregon. There's warmer air here south of where this warm front kind of connected into it. So there's warmer air coming in from California, and this colder air coming in behind it. So you can see with all that here, you have colder air moving into cooler air. Thermal troughs of low pressure, we get these over the southwestern US and down over western portions of mainland Mexico. If you're heading down to the Baja, a lot of thermal troughs of low pressure out there. They're elongated areas of low pressure. They form when there's a lot of hot, dry air that's rising over inland areas. And as they interact with highs off to the west, typically over the eastern parts of the Pacific Ocean, they can produce some rather gusty winds when they interact with it. And on a surface map, they're shown as a dashed line, either brown or orange kind of color, depending on the surface map that you see. In this case, in this example here, you can see that trough of low pressure here, located over southern portions of Oregon and into western portions here of Arizona. So this is where there's been a lot of hot, dry air, and it's a typical location that you find it. You also get them across the Sacramento Valley. During some of the fall months in the September, October timeframe, these thermal troughs of low pressure can sometimes be pushed all the way to the coast. And when that happens, that's when you have your really warm, dry, sunny conditions across the central parts of California, or when you can have some of the Santa Ana winds that can develop out there as well. It also can be a good time to travel north and south along the coast, if you're motoring at least, because there's usually not a whole lot of wind that we usually would see along the coast. So if it shapes up right along the immediate coast, it can give you a lot lighter winds. You want to kind of have that trough. You're looking to sail, depending on what direction you're going into. You don't want to have it too strong because it can produce, if it's just inland and it's pretty strong, high pressure off to the west, the combination of the two of them can produce some really strong gusty winds up near Cape Blanco and Cape Mendocino. Now, another thing that we might see on some of those weather maps are wind barbs. And these will be typically found on surface charts, and they can indicate the wind speeds and the direction that the wind is coming from. One thing to remember for winds is it's always the wind where the direction is coming from, not where it's going to. And you'll see these lines here that will show up here on the surface map. So you're going to see what they call a wind barb, and you're going to see kind of a line here and these feathers on it. When you see a longer line on here at the end of it, that means it's 10 knots of wind. When you see a shorter one, it's 5 knots, and they're going to go in 5-knot increments. In this case here, this example, that the winds are coming out of the west, here at 15 knots. So it's a west, it's coming in from this way. If you look at, kind of west, north, east, and south, you can kind of see how it's coming in from that. And again, they're in knots, which is about 1.15 miles an hour. When you get to winds over 50 knots, that's when you get a flag that will show up here on there. So that's a 50-knot wind showing from the south here, because it's coming in from the south at 50 knots. And you can also combine them as well. So if you see it coming in this case here from the southeast, and you're going to see a flag and 2 long lines and then a shorter line, two long barbs here and then a half barb, kind of add that all together. So 50 knots plus 10 plus 10 plus 5 equals 75 knots, and not something you want to be out in. The Beaufort scale, that's still in use. It's a good way to kind of estimate wind speeds and directions based on the effect of what those winds will do on the ocean surface. So if you look at the Beaufort scale going from 0 to 12, if it's force 0, it's calm, it's like a mirror, it's like glass. You can see that sometimes in some mornings, and it goes on from there. So the higher the number that goes for the Beaufort force, you can kind of estimate your wind speed. So if you're ever out at sea and your anemometer fails, you can still estimate the winds based on what's taking place. So you can look at like 20 knots of wind equal moderate waves, 1.8 meters, white horses on the water. Call that a fresh breeze. And a lot of times when we're talking to our clients about forecasts, we're going to be using kind of, some of these terminologies: gentle breezes, moderate breezes, strong breezes, to kind of explain a little bit about what's going on out there, out at sea. So it's a good scale to have. You can kind of save it here, print it out, or look at it online. And we have that Beaufort scale here kind of showing you for examples of that. Now, using a barometer measures air pressure, and that is measured in millibars. And there are some rules to follow with that. It's a good thing to have on your vessel if you have a barometer out there. Just some simple things to look at. It's a little old school technology, but it still works, and it's a good thing to have. With pressure, it's the 1, 2, 3 rule. So if the air pressure falls 1 to 2 millibars in an hour, in 3 hours, it means use some caution. Could be a storm system moving your way. If you see there's a 4, 5, 6 rule that the pressure falls 4 to 5 millibars within 6 hours, that means that major changes or worsening weather is coming. So if you see a big pressure drop coming your way, that's when you need to take action, that something might be coming your way, and then it might be a good idea to either change course or head into shore. Now, buoy reports, these are available worldwide, although usually the US, Canada area has some of the greatest amount of data available for everybody. They are quality controlled, they're worldwide, they show the location of the buoy, they show wind speeds and gusts, significant wave height, dominant wave period, mean wave direction. They show air pressure, temperature, dew point, and water temperature. And on the National Data Buoy Center website here, you can take a look at that here at the top, ndbc.noaa.gov. It's a free site, it's NOAA. Go on there and pull up buoys anywhere you'd like. And it's a great tool to kind of take a look at what's going on out there before you head out, and kind of look at some real-time observations that are out there. So in this case, this buoy was located, gives you the latitude and longitude, tells you the date and time of the report, tells you the wind direction, wind speed, what the gusts are, significant wave height. And then there's the dominant wave period. Then you have the average wave period. So dominant wave period is pretty much the, if you look at the swells out there that have the most power to them, what's the average, what's the domination of those? About 7 seconds apart. The average wave period, if you kind of look at all the waves going through and average them all together, it's at 5.7 seconds. You can look at the mean wave direction here coming in from the northwest, air pressure, and temperatures of the air and the sea. So all these buoys out there, you can get a lot of great data, and you can also click on history and details to see how things have been changing, because this shows you what is going on right now, but it might be a good idea to see what was out there before. And then this is an example of that. Once you click on the buoy details, you're going to get one of these other charts that are going to pop up and show you the trend with wind speeds and directions, wave heights and directions over a period of time. So in this case here, this example from October, you can see that at 10:50 a.m. Pacific Daylight Time, you can see what the wind speed was, about 9.7 knots and gusts of 12. But you can look back at time at 4:50 in the morning where it was about 15.5 knots for the wind speed and 17.5 knots for the gust, and see how the wave heights have changed. So take a look and kind of look your way up here for the most recent. And in this case here is a little bit of a building trend in terms of the waves. That gives you an idea, okay, have the swells and the waves been increasing? It gives you an idea kind of looking at the trends, or has it been pretty steady? Like in here, it was all pretty much within the same heights. This is another example of the details that are in there, and some of these buoys will even tell you the steepness of the waves. So, when you look at wave periods, if they're long in period, 13, 14, 15 seconds, the kind of waves surfers like, nice long period ones are going to be average or low. When they're short period and they're coming in pretty quickly here, then that's when things are going to be steep. So that's also an importance to know about. Obviously, you want to try to avoid trying to be sailing into steep, short period seas on the nose. It's definitely not a comfortable experience at all. And you can see the periods on these 3, 4, 5, 6 seconds. That's pretty short. So that's why you're getting steep to very steep. That's out there. Now, when the wave height drops, even if the period still stays short, it can be a little bit easier to handle. So in this case, here down to the lower part of this chart, you see the wave height at 1.6 feet, and the period is running at about 4 seconds apart. So that's a little bit better than when it was, that's average. But when it's over 2 feet for 4 seconds, it's going to be pretty steep. Ship observations, these are available on some different websites out there. Sometimes they're not quality controlled. It just depends on what how the vessel is reporting it. Buoys are quality controlled. Ships aren't necessarily quality controlled. Locations can change, of course, because ships are moving, so they are changing. But they can show winds and directions. They can show wave heights and periods in there as well, pressure and visibility. So there can be some good details in these, but whenever you look at a ship report, always look at it with a grain of salt. On occasion, they could be taken from a much higher vessel up at bridge level, as opposed to near the surface where most pleasure craft are going to be. So you kind of have to look at that and kind of determine, okay, does that wind speed make sense? Are there other reports out there that show it, or is it way out of whack and it's showing 35 knots? In reality, it's only 10 knots out there, for instance. Satellite-derived winds. This is a pretty cool tool that's out there. We have polar orbiting satellites, one of which is called the ASCAT, and it goes around the Earth twice every day, and it does these swaths, these paths that go across the Earth. And what it's able to do is scan the surface of the ocean and determines what the wind speed and direction are based on those based on how the surface looks like when it scans it. And doesn't get every part of the globe, and there's going to be some gaps within it. But when you go to the ASCAT website, you can be able to pull these up, and it's really a good tool to kind of get a good idea of what's going out there when you don't have as many ships or buoys or other observations. So in this ASCAT pass here, where we talked about those wind barbs, you can see them with the long feather here, so that's 10 knots of wind. It also matches up with the colors up here on the right too. This is for the Baja, so if you're heading down to the Baja or Cedros Island, Turtle Bay, where a lot of vessels fuel up down here, you can see this was kind of getting towards the middle part of the day, and you can see some of these winds kind of wrapping around here south of 30 degrees north, and they're kind of being enhanced a little bit. So you're seeing some 15 to maybe as high as 20 knots of wind here in this section. So kind of with the heating of the day and the land mass here, that's where we're getting some of those funneling winds. So it's kind of a neat tool to look at here to give you kind of an idea. It tells you the time here on the bottom, and this time is in Zulu time. So for Pacific Daylight Time, you'd be taking 7 hours off of that. So this is looking at 5:12 p.m. Zulu time, but it would be 10:12 a.m. Pacific time. So you always got to kind of be careful with all these different times out there. Good thing is at the top, it also shows you an example, UTC, Greenwich Mean Time, Zulu time. They're all the same, and give you an idea of whether it's local time or Zulu time. But a lot of things in weather for observations are all taken in Zulu time just to make them consistent around the globe. Radars, we take a look at radars. Radars indicate precipitation. They also indicate intensity and movement. And the hotter or warmer the colors are, the more intense the precipitation is. Orange and red are likely to show some thunderstorms. Now, we don't get a lot of thunderstorms on the West Coast, but they do happen on occasion. So I thought I'd show an example here. This is off the coast of Texas and Louisiana, just to show you a radar image here showing where the area of precipitation is. And this is taken from the weather.gov site, and there's other sites too that you can check precipitation out there on radars. But where you see these really bright kind of red colors kind of look like cells, you can kind of see that. These are definitely thunderstorms that are going to be out there. Where you see this kind of broader, darker green, maybe a few yellows in there, it's more what we call stratiform precipitation, kind of some older areas that have kind of consolidated together, and it's more lighter to moderate precipitation taking place. And you can animate radars. The one thing to remember is when you animate a radar is that it's showing you where the precipitation has come from. It's not showing you where it's necessarily going to be in the future. It can show you a direction that it's moving towards, but the moment you hit the present time, that's all you can infer from that. You can't assume that that precipitation is going to keep moving in that direction in the same shape that it is then at that time. There's an example again of where those thunderstorms are. In the US, there's 160 radars approximately, and they're in all US states, all US territories. They're definitely pretty variable elsewhere in the world. Some countries have really good radars, some have them good along the coast. Canada has some pretty good radars. Mexico, it's much more spotty. Other countries kind of have them kind of hit or miss, but different countries' weather services may have their own radars available for you to look at if you're traveling out of the country. In the US, the radars have a 290-mile range. That is, unless they're backing up against a mountain or a mountain range. So that's something to consider as well, that they're not going to be able to see out as far, but when they are on the coast, they can definitely have that pretty good range out there to see precipitation well out in the distance. And they can also indicate tornadoes and water spouts if you're traveling in more areas that are more prone to get those. This is an example here of a thunderstorm here that had a hook echo to it here, kind of coming into the coastline. And kind of showing a potential tornado here with this strong thunderstorm here. You can see this kind of a hook shape. So these radars can certainly show the location of where these tornadoes might be. But typically, you're not going to be needing to worry about trying to analyze the radar data while you're out at sea to see if there's a tornado in it. Usually, if there's radar data, then there's probably going to be a government institution there looking at it, who'd be sending out watches and warnings appropriately here for it. But I just wanted to show you on this radar what this tornado looks like. You can see it kind of rotating into here. And this is where the tornado would most likely be located, right there. Satellite imagery. Satellite imagery can help to determine sky conditions at the surface. As meteorologists, we look at these all the time to see, okay, is it going to be cloudy? Is it going to be clear? Is there going to be fog out there as well? Satellites have different channels out there, as we call them, where they're able to see different features with the clouds. They have a visible channel, they have an infrared channel, water vapor. I'll tell you some examples of those here coming up. They're used to find areas of fog, thunderstorms, and other weather features. And they can also help to find outflow boundaries, which can produce gusty winds. And I'll show you what some of those look like as well. It's good to have a general broad knowledge again of all these different weather features. Some of these may not apply as much to the West Coast, but if you're doing any traveling or sailing around the world, it's good to at least be kind of familiar with some of the terms and some of the technology that's out there, so that if you do go sailing somewhere else, that you'll be able to identify a couple of these other weather features out there. So with visible imagery, the clouds are illuminated by sunlight. So it's in space. It's essentially as if you were out there just taking a picture with your camera. It's in the visible imagery, so it's coming in at that range. Because of that, it only is available sunrise to sunset. So in the middle of the night, you can't have any visible imagery. You can see different types of clouds on there. They've gotten some really tremendous resolution improvements with some of the new satellites that have been launched in the last couple of years. There's a website, GHCC. That's a NASA one. You can search for that on Google. That's a great resource out there that can help to find some good satellite imagery with that, because you can kind of customize it, click around and zoom in and zoom out and be able to see different parts of the world out there for different kinds of satellite imagery. You can also see the structures of thunderstorms within these satellites. So they're really good, these visible satellites, compared to where they were not even all that long ago. So there's a lot of stuff going on in this satellite imagery here. For an example, we're able to see some thunderstorms and an outflow boundary. So there's an outflow boundary right here. So we have thunderstorms here off to the north. In this example here, you can see how kind of lumpy and bumpy they are. There's definitely some storms going on within those. There's also a lot of high upper level winds. You can kind of see it kind of moving the high clouds here off to the west within this visible imagery. Then you can see these thin lines that are coming through here. These are outflow boundaries. So once thunderstorms get pretty strong, eventually they'll collapse. And as they collapse, all that cool air, that moist air will hit the surface of the ocean, and then they'll kind of spread themselves out. So if you're ever sailing and you go through one of these outflow boundaries here, you can have a rather sudden, sharp increase in the wind. And because it's traveling well out ahead of the thunderstorm, you might kind of be scratching your head and saying, where the heck did that come from? Because there's no storms that are visible, or if they are, they're well in the distance, and all of a sudden you get this sudden sharp wind shift and increase in the winds as well. So they can propagate out for dozens of miles, or 1,500 miles in some cases, away from the thunderstorms. And we've definitely had some clients go through some of these and warn them about it and say, hey, you're going to get one of these outflow boundaries. And sure enough, they're sailing and everything's, pretty good. And all of a sudden they get a gust of 30 knots, for instance, within them. If you loop these images, you can actually see them as they move by. Again, there's the thunderstorms off in that area. Now, the visible satellite imagery is also pretty good at locating areas of fog. It's a visible imagery again, and fog is going to show up really nicely here along the coast of California. So when you pull up the visible imagery, kind of zoom in on it, you're going to look for where you're going to see these kind of gray areas here that are kind of smooth and continuous, and these are fog banks, or at least low clouds. You can really see how they're right along the coast too. You can kind of see that really thin line there right along the coast, showing the fog that's right along the coast. And how many times in California, if you're on the coast, it's kind of cool and foggy, and you just go inland a couple miles and it's warm and sunny. And certainly in this case here with this silent imagery, there is definitely no clouds going on over central portions of California. So some patches of fog and low clouds that are out there, but visible imagery is really good to be able to help detect that. It's the best one to try to find some of these fog areas when you have nice clear skies around it, but you kind of see coming out of San Francisco Bay, where are the boundaries here of the fog banks. Infrared satellite imagery, that is used to measure cloud temperatures. Good thing about infrared imagery is it doesn't take a break at night. It's available 24/7, but it can be harder to see some of the fine scale features within some of those infrared imagery out there. So the visible does a really good job of being able to detect it, but the infrared imagery is going to be a little bit harder to see some of the fine scale features. But it can also help find some features a little bit easier too. So we have thunderstorms here that are showing up in this infrared imagery. And again, if you do any sailing down the Baja towards Mexico, this is a whole big cluster of showers and thunderstorms. And if I was watching this, I'd be a little bit concerned about some potential tropical development taking place within this cluster here as well. So the satellite imagery is pretty good at being able to detect areas of thunderstorms and areas of convection of storms. You can also use it to help to try to find some areas of fog and low clouds too, because you can kind of see it's kind of fuzzier and gray out here. West of the Baja, this is definitely a big area of fog or low clouds. So we'll talk a little bit here next about cloud progression. This is just kind of reading the skies, kind of looking at how the skies will change with clouds out there, and kind of learning how to read the clues in the sky. They can help to inform you of upcoming weather that might be taking place. And the phrase, as everybody knows, red sky in the morning, sailors take warning, red sky at night, sailors delight. Reason why that's a very broad way to kind of look at things, but at least is sometimes accurate. So when you see a red sky in the morning, typically that means that you have some sunshine in the eastern part of the sky coming in from the morning where the sun is, and then you have more clouds off to the west being illuminated by that sun. Most of the time the clouds move from west to east, so you're seeing the direction of the clouds are moving into. If you have a red sky at night or at sunset, you're going to have more sunshine in the western part of the sky. You're going to have more clouds in the eastern part of the sky. So that with the flow from west to east typically means more sunshine or clear air is trying to move in for the evening. There's some clear skies for the night, which would give you a little bit of a break in some of the weather out there. Now, there's all kinds of different clouds, and we're just going to hit on a few of these here for you. And when you see cumulus clouds, everybody's seen these. These are the clouds that everybody kind of can look up to and think that they certainly look like a dog or a cat or something like that. People play that game of trying to see what they look like in the sky. These are fair weather clouds. Typically when you see these, it's a nice day out there. They're very picturesque. They're shallow, they're low-level clouds, they're not all that high up in the atmosphere. They indicate fair weather, and they're also signs of limited moisture because even though there's enough moisture for the clouds, it's not as much for them, in this case here, for them to develop substantially. However, if conditions are right, the clouds can continue to grow. They can kind of combine, and we get more moisture out there, and they can form into cumulonimbus clouds. And that's when we see our thunderstorms. These will cause squalls, potentially water spouts, tornadoes, and they have an anvil shape to them as well. So you can see in this case here, all the low-level moisture is starting to continue to rise up to the atmosphere. It's reaching a certain altitude here and it's fanning out, and then the high-level winds are starting to spread this system out, almost as like an atomic bomb. But it is a thunderstorm out there, and we see these all the time, especially when you're traveling more tropical areas. They're going to tend to get more thunderstorms. You don't see these as much in California, not very often, unless you're heading over into eastern parts of the state when we get some monsoonal moisture that comes in during the summer months and get some of these anvil-shaped clouds out there. Certainly, that's a sign that you want to try to avoid them if you can. A lot of people that are sailing, let's say out of Florida, you're going to see those almost on a daily basis each afternoon forming over land. When that takes place, eventually they can move back out closer towards the coast. Now, ahead of large-scale storms, so when we have lows and fronts out there, there's a progression of clouds with that as well. So out ahead of it, as things start to change here, well out ahead of the storm, you see some cirrus clouds coming in. These are high-level ice clouds, and the clouds consist of ice, and they increase in moisture, increase intensity as the moisture increases with them. So in this case here, these clouds are probably moving in this direction off to the right, and you can see that the progression of the clouds here, see how it gets thicker and denser here off to the south and west. That typically means that we're going to see more moisture coming in from that direction. So they tend to kind of thicken up as the storm comes through. Altocumulus clouds, these occur after those cirrus clouds come in. Typically, we can see these in the morning hours. They indicate a lowering cloud base because the cirrus clouds go pretty high up in the atmosphere, 25, 30, 35,000 feet. These are starting to come down into about 20,000 feet, 15,000 feet. And it also is a good sign to say that, hey, precipitation could be starting within about 12 hours. Nimbostratus clouds, this is essentially when precipitation is occurring or it's imminent. A lot of times you can kind of see it coming because you can actually see the rain being from the precipitation emanating here from the clouds. As they come through, you're getting lower visibility, you're getting fog. You can kind of see that here. It's definitely not as clear as those other photos. And when the visibility will increase, the precipitation will decrease. So all of a sudden, if you start to be able to see features in the distance, your horizon is becoming more clear. You can see mountains if you're on land, for instance. That typically is going to mean that your precipitation is on the decreasing trend, at least temporarily. Quick little talk here, a little bit about ocean currents. These are what we're considering to be large-scale currents as opposed to tidal currents. They're going to vary with weather features and wind. They can be affected by those. If you have a prolonged period of wind blowing for a certain long period of time, it will start to create some local currents on the surface. There's major currents. People have heard of the Gulf Stream. On the eastern part of the U.S. Those are a lot slower to vary, but they can meander like a river and have currents that can kind of break off and change with those. And currents can be highly variable over a short distance. With the Gulf Stream, there's often times if you're going to be sailing and crossing it, that it's a pretty instantaneous effect when you first hit the stream, and you can see a drastic increase in the currents and of weather patterns out there as well. Different temperatures within the currents as well. It's being a warm current. Ocean currents and the South Equatorial Current, I wanted to show an example of that here just to kind of show you one of those. This is another larger current out there. It's often in the South Pacific here. Here's the equator. And it can meander a little bit north and south. The South Equatorial Current, you can see the direction that's flowing in here from east to west. And you can see in this large-scale current that's out there in the South Pacific. Again, this is just one of the currents that are out there. You can see in parts of it actually can get up to almost 3 knots of current. So if you're sailing and you're heading down to the South Pacific, you'd want to be able to prepare a route that's going to take you and try to utilize this current as much as possible. You can get a 2 or 3 knot current boost for a long period of time. You can make a lot more progress that way and really have some good speed over ground in that case. You wouldn't want to be sailing, though, the other direction and trying to sail into it, because then it would be substantially slowing you down and not causing you to get any kind of benefit from that. And you can have some great winds, but you're not making much forward progress because that current is pushing against you up to 2 to 3 knots. So it's a lot of strategy when we do our routing. You know, how can we get people to cross the currents at the best angle, as fast as possible, or in some cases to stay in them as long as possible to take advantage of them. Sea surface temperatures, these are also able to be pulled up on different sources out there, and it's a good way to be able to determine what the sea surface temperatures are and different boundaries out there. This is the same current out there, and it actually shows a lot of cooler temperatures, looking at the scale here, about 22, 23 Celsius temperatures in the low 70s, mid 70s out there. In this case, South America is kind of out over here. And there's been some upwelling. So it's kind of the same case again off the coast of California, why you have such cooler water out there. And the current here is kind of taking that water, moving it off to the west. And gradually, as it's in the tropical sun, it will gradually warm up. And the farther west you go, you can actually see how much warmer it gets. In the northern hemisphere here, where the current's going the opposite direction, it's bringing in a lot of warm water off to the east, and you can see some peaks in here running up to nearly 30 degrees Celsius or 86-degree water temperatures. So some rather big temperature changes depending on which way the currents are going. As we start to finish up the presentation, we always talk about professional sources. So whenever you're going to be looking to do a weather briefing or use weather sources, it's always important to kind of look at, where are those sources coming from when you're planning a trip. And knowing, first off, a few of the things that I showed you. I know there was definitely a lot of topics to go through. Just having a general, very basic weather knowledge can certainly help to understand where some of the weather terms are coming from, how do they apply to your situation, those kinds of things. Also, it's important to know to plan the best climatological times to do a transit. To know, for instance, that obviously you probably don't want to try to sail up to Seattle in the middle of January, but then, when is the best time to go north or south? When's the best time to go to the Baja? Should you go in the summer? Should you go in the winter? What's the weather going to be like for that? So kind of knowing the best climate of those areas can help plan the trip and make it successful so you don't go out of season. You also, professional sources out there, they can help you find weather windows to go. And they can also help you out with those kind of climatological reports that I talked about. Other sources out there when using a weather router can help you being updated while you're underway so that you don't have to keep checking everything. They can stay in touch with you. It's also a lot of different companies provide an extra pair of eyes, on land. So they're kind of making sure that you're going to get to your destination safely and be able to watch you there closely. And again, when you're looking at your sources, you want to look at the reputation of the weather provider. Are they really dedicated to the science of meteorology? How accessible are your sources? Are they online? Are they in person? Are they emailed to you? How can you reach them? Are they reliable? Do they have a good track record? And then to be careful when you're looking at television weather sources, because some of them may not be all the best. There's some of the sources on TV are not necessarily degreed meteorologists, so you want to be careful with that. And a lot of times their marine weather forecasts are very, very brief. They're focusing much more on land because that's where all of their viewers are. And yes, they have viewers that go out to sea, but typically their marine reports are pretty brief. They may just have 1 or 2 days of that. And sometimes they're not scrutinizing it as much as other sources might. So some final conclusions here. Hope you learned a few things here about weather basics. Again, I know it was kind of a lot to cover, but it gives you at least a taste of some of these things. You can kind of learn very broadly about weather. There's definitely ways you can learn more details about these different weather systems that I talked about, reading weather maps, but I wanted to give you at least a brief idea of how to kind of do that a little bit here on your own. Knowing a little bit about climatologically what the weather is, that can be great to know because that can help you plan when you're doing a trip somewhere, or if you're going to be flying somewhere and chartering a sailboat for a week, for instance, in a different part of the world. You kind of want to know what the weather is typically going to be there because that can make or break your entire trip. It's a good idea before you head out to start looking at the weather patterns. a week or so in advance. That starts to give you an idea of what's been happening, what's coming your way, and just kind of know that changes can be expected within those. You should also, know when to seek professional guidance out there. If you're doing a big trip, you might want to have some professional assistance with that to make sure it's successful. If you're doing a short trip, you may not need it as much. And you also need to know when not to push your limits. Know the limits of yourself, your training, your experience, and your vessels, so that you don't get into a weather situation that you're going to regret in. It's always better to have stayed in port and missed out on a trip than to be far out at sea in a bad situation that could have been avoided. And then you're going to be in trouble with that. So that's what we always tell people, know when not to push the limits, know where you're at. We know that everybody has a wide variety of backgrounds and experiences. So just know those, know what they are for the crew, and that can just make for a good trip no matter where you go in the entire world. So with that, that is the end of my presentation there. If you have any questions about weather routing or myself, you want to ask me any questions, I'll be happy to answer them. Just attention to Jeremy Davis there in the email, but you're welcome to send me any weather questions you have, and I'll be happy to help you out with that, or if you had any voyages that need assistance with. So with that, I'll conclude the webinar.
Thank you, Jeremy, and to everyone who has joined us today. You can see more of Sail America's 2020 Pacific Sail and Power Boat Show Seminar Series in our virtual seminar library at pacificboatshow.com. Thanks, everyone, and you have a fantastic day.